Hello friends, today's question. So we are going to solve some 2019 mains question, and in the first question it is given that a circuit connected to an AC source of EMF E0 sin 100t with t in seconds gives a phase difference of pi by 4 between the EMF E and the current I. Which of the following circuits exhibit this? So basically we have two types of circuit given in the options, RC and RL, and value of resistance in for each option is same, whereas the value of inductance is and as well as capacitance is different. And we are given that the phase difference should be pi by 4. So phase difference basically means that we are given tangent of phi. This is our phase difference, and here value of phi is given as pi by 4. So in this case we are going to take options one by one and try to find out what will be the phase difference for the resistance RL circuit as well as the RC circuit. So let us start first of all with our RL circuit. And for RL circuit, the phase difference, that is our tangent of phi, it is given as XL upon R, and XL is our omega L, so we can write this as omega L upon R. And we are also given the equation of the EMF, which is E0 sin 100t. So this value of 100 is nothing but value of omega. And we are given that this phi is pi by 4, and we can deal it with later on. And for our RC circuit, the phase difference, that is tangent of phi, it is our XC upon R, and which comes as 1 upon omega CR. And value of R is same for each options. So R is basically given as 100 kilo ohm, which is nothing but our 1000 ohm, and value of omega is our 100. So let us take option number 1, or option A rather. In option A, value of R is our 1000 ohm, and we are given capacitance of 1 microfarad. And we can find out the phase difference. So you can say that tangent of phi is our omega, it is omega C. So this is 1 upon omega CR. We substitute the value, and 1 upon omega C will be coming as, this will be coming as 10,000, and resistance is our 1000. So this will be equal to 10. So from here we can say our phi is approximately equal to close to 84. So obviously the phi is not equal to 45 degree. So this option is incorrect. Now let us take option number B. Value of R is our 1000 ohm, and we have value of inductor is 1 millihenry, and similarly we are going to find out tangent of phi, or rather we can say phi. So we can say tangent of phi is equal to XL upon R, which is equal to omega multiplied by L. So this comes as omega L upon R, and omega is our 100, and this comes at 10 to the power minus 3, and this is our 1000. So we get this as 0.001. Therefore, phi will be approximately equal to 0.0057. So this option is also incorrect. Let us take option C. Value of R is our 1000 ohm. And in option C, we have capacitance as 10 microfarad. So once again, we are going to use formula tangent of phi is equal to XC upon R. And XC will be equal to our omega C. Omega is our 100, and this is 10 into 10 to the power minus 6. One upon like this, and this will be coming as equal to XC will be our 1000, so XC we get this as, so this will be coming as 1000 divided by 1000, and this will be equal to 1, which gives us that phi is equal to 45. And this is a single correct option. We are left with one more, D. So let us solve for D also. We have option D. Value of R is our 1000, and inductor is our 10 millihenry. So we can write our tangent of phi is equal to XL upon R, and this XL will be equal to our omega L. Omega is our 10, and this comes 10 into 10 to the power minus 3. So we are going to get XL will be equal to we substitute the values. Is 10 into minus 3, so let me write it. This comes as 1000 and multiply by 1000. Sorry, here it is 100, my mistake. And this cancels out, so this becomes as 1 upon 1000, or we can write this as 0.001, and this gives us that our phi will be approximately equal to 0.057. This option is also incorrect. So only option correct is option number C. Option C is correct. Let us take next question. The next question we are given that we have a alternating source Vt and which is governed by the equation 220 sine of 100 by t. Volt is applied to purely resistive load at 50 watt. The time taken for the current to rise from half of the peak value to the peak value is. So we are going to find out the time required for half to peak value. So first of all, we are going to determine what will be the peak value of the current, and we are given the equation, and the given equation is our Vt is our 220 sine of 100 pi t, and it is a purely resistive load. Okay, and the resistive load is of 50 ohm. Sorry, here it should be ohm, not watt. So we have a resistance of 50 ohm. So let us determine first of all the peak value of the current. Peak current is our I naught, which will be equal to V naught divided by R, and V naught is our 220. So we get this as 220 divided by 50, and this will be coming equal to as 4.4 ampere. So this is the peak value of the current. Now we can express the current also as a function of time. So you can say current as a function of time, and that equation can be written as I of t, peak value of the current, that is of I naught, and sine of 100 by t. As it is purely resistive load, so there will be no phase difference between the voltage as well as the current. We substitute value of our I naught, which we found as 4.4. So this becomes 4.4 sine of 100 by t. And let us find out the time when the current is half the peak value. So we say the time, let us suppose that time we call as t1, when the current is half of the peak value. Peak value. Therefore, we can write it as I of t1, and this will be half of the peak value, and the peak value is our 4.4. This divided by 2, and we get this as 2.2 amperes. So we found out the value of the current IT1, and we can modify. Let us call this as equation number 1. So we can write thus the equation 1 at time t is equal to t1, current is given as half, so we get this as 2.2 is equal to 4.4 sine of 100 by t1. Now it is simple calculation, and this can be written as sine of 100 by t1 will be equal to 2.2 divided by 4.4, which gives us 100 pi t1 is equal to sine inverse of this comes as 1 by 2, that is 0.5, which comes as pi by 6, and this pi and pi cancel with each other. So from here we can say that our t1 will be equal to 1 upon 600 seconds. So we found out the time t1 at which the current is half. Now we are going to find out the time at which the current is having a peak value. So we say time, let us suppose that time is t2 when the current is at peak. So the current at the peak, we can write the equation 1. So you can say from equation 1, for this peak condition, sine of 100 pi t2 should be equal to 1. And this gives us that our 100 pi t2 sine inverse of 1, and this will be over pi by 2, and pi cancel with each other. This gives us t2 is equal to 1 upon 200 seconds. So we found out the time at which the current will be half of maximum value and the time at which the current will be maximum. And finally, we are going to find out the time difference. The time difference, let us call that as delta t, and that will be equal to t2 minus t1. This is 1 upon 200 minus 1 upon 600, and you can say our delta t will be equal to, this will be 2 upon 600, which comes 1 upon 300, and approximately this will be equal to 3.33 milliseconds. So this is the time taken by the current to rise from half of the peak value to the peak value. So the option that is our option number D is the correct option. Option D is correct. Now the next question. We are given that in the verb circuit, C value of capacitance is root 3 2 microfarad, R2 is, sorry, here also it is ohm, not watt. Inductance is root 3 10 Henry, and R1 is also 10 ohm. The current in LR1 path is I1 and CR2 path is I2, and the applied voltage of AC source is given by V20 square root of 2 sine of 100t. The phase difference between I1 and I2 is. So this is our basic schematic which is given to us, and we are having R2 and C is in series with the current I2, and R1 and L in series with the current I1, and we are supposed to find out the phase difference between the I1 and I2. So we start with the given equation, and we have the given equation as V is equal to 200 square root of 2, and this is a sine of 100t. From here we can write that our frequency, that is omega, is equal to 100. So First of all, let us consider this path, LR1 path. For LR1 path, and we can find out its inductive reactance, that is our XL, will be equal to omega L. Omega is our 100 and value of inductance is given as root 3 by 10, and this comes equal to as 10 root 3 ohms. Now we can find out the impedance. So we can say the impedance, let us call that Z1, will be equal to R1 plus JXL, and we can write, we substitute the value, we get this as 10 plus J, and here we have 10 square root of 3. We can find out its magnitude. So we can say our impedance Z will be equal to, this comes as 10 square plus 10 square root of 3 and its whole square and the square root. We get this as 100 plus this will be our 300 square root, that is square root of 400, which comes as 20 ohms. Therefore, we can find out the phase angle now. We can say the phase angle, let us suppose that is our phi1 for current I1, and that will be equal to phi1 is equal to tangent inverse, and we have XL upon R1. We substitute the values, we get this as tangent inverse. XL is our 10 square root of 3 divided by 10, and this comes as tangent inverse of square root of 3, which is our 60 degree. Now same calculation we are going to do it for the second path, that is CR2 path. For CR2 path, so first of all we are going to find out our XC. XC will be equal to 1 upon omega C, and that will be coming as 1 upon omega is our 100, and capacitance is given to us as 2 square root of 2 microfarad. 2 and 10 is to the power minus 6. So this gives us that our XC will be coming equal to as 20,000 and divided by square root of 3 ohms. Similarly, we can find out the impedance Z2, and Z2 will be equal to this R2 minus J XC, which comes as 20 minus J, this is about 20,000 divided by square root of 3, and we can find out this magnitude. So impedance will be equal to, and this will be approximately coming equal to 11547 ohm. Finally, we can find out of phi2, that is a phase angle, will be equal to tangent inverse of minus xc upon R2, and this we substitute the value, we get this a tangent inverse of minus 20,000 divided by square root of 3, and it is 20. So phi 2 comes approximately equal to as minus 89.99, and we are supposed to find out the phase difference. You can say phase difference, let us call that as delta phi, between I1 and I2. We get this as phi 1 minus phi 2, and we just calculated our phi 1 and phi 2. Phi 1 was 60, and this becomes minus minus plus, and we have 89.79, and this comes approximately equal to 150 degrees. So this is the phase difference between, approximately phase difference between I1 and I2. And in this case, none of the options is the correct one. So here the correct option should be our 150 degree. So let us take next question. We have a solid metal cube of edge length 2 cm is moving in the positive y direction at a constant speed of 6 meters per second. There is a uniform magnetic field of 0.1 Tesla in the positive z direction. The potential difference between the two faces of the cube perpendicular to the x-axis is given by. In this case, we are supposed to find out the potential difference. So first of all, we are going to find out what will be the induced EMF, and that induced EMF we also call it as a motional EMF. So we say that induced EMF, or it is also called as a motional EMF, and this is given as E is equal to BLB, where B is the magnetic field, L is the length of the edge, and V is the velocity. And the potential difference we are supposed to find out the potential difference. So you can say that the potential difference which is, let us suppose, given as V is equal to B, and the edge is suppose given as A, so BAV. So we substitute the value, we get this as V is equal to magnetic field is 0.1 and edge is given as 0.02 multiplied by V is the velocity, that is 6. So we get V is equal to 0.12 volt, or we can say that our V is equal to 12 millivolt. So we get option number B is the correct option. Option B is correct. And next question is about the transformer. So we are given a power transmission line feeds a input power of 2300 volt to a step down transformer with its primary windings having 4000 turns. The output power is delivered to a 230 volt by a transformer. If the current in the primary of the transformer is 5 ampere and the efficiency is 90%, the output current would be. So in this case, let us find out first of all the input power, and then using the efficiency we can find out the output power, and that is going to help us in finding out the output current. So we start with the input power. Let us call that as P in, which will be equal to voltage in the primary multiplied by the current in the primary. So we get this as P input is equal to 2300 multiplied by 5 ampere, which comes close to 11,500 watts. And we can find out now output power because of the efficiency given to us. You can say the output power, you can write it as efficiency is equal to P out upon P in. So we can write this as now as P out is equal to efficiency multiplied by P input. Efficiency is given as 90%. This is 0.9 multiplied by 1150, and this will be coming close to as 10350 watts. So this is our output power. Now we can find out our output current. And for this we are going to reduce the relationship. P output will be equal to voltage in the secondary multiplied by current in the secondary. So we get this as IS will be equal to P out divided by voltage in secondary, and P out is our 10350. Secondary voltage is given as 230, and this comes as close to 45 amperes. So we have current in the secondary will be equal to 45 ampere. That is option number A is the correct one. Option A is correct. So the next question, it is given that we have a thin strip 10 centimeter long is on a U-shaped wire of negligible resistance. It is connected to a spring of spring constant 0.5 Newton per meter as in figure. The assembly is kept in a uniform magnetic field of 0.1 Tesla. If the strip is pulled from its equilibrium position and released, the number of oscillations it performs before its amplitude decreases by a factor of E is N. If the mass of the strip is 50 grams, its resistance is 10 ohm, and air drag is negligible, the N will be close to. So we are given this figure, and we have a strip which is connected by a spring, and the spring constant is given by 0.5. And if it is moved from its equilibrium position, and it says that the number of oscillations performed, amplitude starts to decrease by a factor of E, and it is governed by a N factor. So we have to find out value of N. So in this case, this entire system is lying in a magnetic field, and the magnetic field is given as 0.1 Tesla. And in this case, as this strip is you can say released from its moved from its equilibrium position, it is going to oscillate because of this spring, and the motion because of this presence of magnetic field, EMF will be induced, and that will be resulting in the flow of the current. And because of that, a magnetic field which is going to oppose the, you can say, it will be acting as a damping factor. So you can say from here that when the strip is pulled from equilibrium, and released, so because of that, the strip oscillates due to spring force. The strip oscillates because of the spring force, and because there is magnetic field present, so we can say the motion in the magnetic field induces EMF. Motion in the magnetic field induces EMF, and this EMF will result in the flow of the current. You can say causing current to flow. And because of this current flow, it produces a magnetic force rather, which opposes the motion. Which produces magnetic force opposing the motion. Or we can also say it as a damping. And in this case, the motion of the strip is along x-axis, and the strip is along, you can say, y-axis, and the magnetic field is along z-axis. So this entire setup is in xy plane, and magnetic field is in the z-axis. So we can write the equation of the motion . So first of all, we can write the spring force . Let us call that Fs, and that will be equal to minus kx. And if we say that the strip moves with the velocity v, then we can write that strip moves with velocity v, and that v can be written as dx by dt. And because of this movement of the strip, the magnetic flux through the loop is also going to change. Therefore, we can say that the flux, which can be represented as phi, will be equal to B, that is our magnetic field, multiplied by area, and which can be written as B multiplied by L and multiplied by X. And next we can write our EMF, which will be our you can say minus d phi by dt. If you substitute value of phi, it can be written as BL, and this becomes our dx by dt. Dx by dt is our V, so we can write this as minus BL multiplied by V. And the current, if we suppose is I in the circuit, so we can say our current, which is our I, it will be given as EMF divided by the resistance R, and EMF is our BLV, and this we get divided by R. Therefore, the magnetic force, which will also, like we said, it will be acting as a damping. Magnetic force, if we represent it as Fm, will be equal to ILB, and its direction will be you can say opposite to the velocity v. You can say direction opposes v. So we can further substitute the values. We can write Fm will be equal to minus BLV divided by R, and here we have our LB, and this can be written as minus B square L square divided by R. Instead of V, we can write it as dx by dt. So therefore, the net force if we represent it as F, will be equal to spring force plus magnetic force, and we substitute the respective values. We get this as minus kx and minus of b square L square upon R, and this comes as dx by dt. And we can write the net force is nothing but our mass into acceleration. So this can be written as double derivative of our small displacement, that is x. So we can just readjust this differential equation, and this can be written as double derivative of x plus b square L square upon mr dx by dt plus k upon m x is equal to 0. Now this is nothing but we can compare it with a damped harmonic oscillator. So let us first of all write the equation for damped harmonic oscillator. We can say damped harmonic oscillator, and the standard form, the equation is given as double derivative of x plus twice beta single derivative plus omega naught square x is equal to 0. And here the damping constant is given as 2 beta. So we can write from here that our damping constant, which is 2 beta, and if you make 1:1 comparison, this comes as b square L square upon mr. From here we can write our beta is equal to b square L square upon 2mr. Next we can write out the natural frequency, that is our omega naught. Natural frequency, which is our omega naught square, this gives us k upon m, and can be written as from here that omega naught is equal to square root of k upon m. Now we substitute the values. First of all, we can find out our omega naught. Omega naught will be equal to square root of k is given as 0.5, spring constant mass is given as 0.05, and this comes close to as 3.162 radian per seconds. Similarly, we can calculate our beta. Beta will be equal to 0.1 whole square, and we have length, that is also 0.1 whole square, and divided by our 2 into we have 0.05 into, I think, what is this, radius? Let me check. Ah, 10 centimeter. Point 1, and this will be coming close to as 0.0001 and per seconds. So we can find out from here damped frequency. Damped frequency, which is represented omega, and given as omega is equal to omega naught square minus beta square, and its square root. And we substitute the value. This value will be approximately, because value of beta is very small, so we can say this is approximately equal to omega naught, and the value of omega naught is our 3.162. Now it is given that the amplitude will be decaying, so we can write the equation for the amplitude decay. And it can be written as x of t is equal to a naught e raised to power minus bt, and we have cos of omega t. And the amplitude, you can say our a of t will be equal to a naught e raised to power minus bt. And it is given that the amplitude decreases by a factor of e. It is given in the question. So we can say from here that amplitude decreases by a factor of e. Therefore, we can write that our a of t upon a naught is equal to e raised to power minus 1 and e raised to power minus beta t. and we already know the, one second, yeah, it is given as E, and we have to find out the value of N. So if we substitute the values, we can say that this will be approximately coming equal to, as, let me sort it out first. So we can just reformulate it as 1 upon E minus beta t will be equal to minus 1, and this gives us our t is equal to 1 upon beta, and if we substitute the values, we can write that t is equal to, because value of beta we already know is 1 upon 0.0001, and this gives us t as 10,000 seconds. And we are supposed to find out the value of N. So for that, we can find out our number of oscillations. So we can say number of oscillations, that is T, will be equal to 2 pi upon omega, and this is equal to 2 pi upon omega is our 3.162, and this can be written approximately as 1.986 seconds. So therefore, finally, the number of oscillations in time t, which we just found out at 10,000 seconds, which is given as n. So you can say value of n is equal to small t divided by capital T. So this becomes 10,000 divided by 1.986, and this comes approximately equal to 5.37.7, and we can approximate equal to as 5,000. So the option that is close to this value is 5,000. So we can say option number C is the correct one. Option C is correct. So we shift to the next question. And next question, we are given that we have a copper wire is wound on a wooden frame whose shape is an equilateral triangle, and if the linear dimension of each side of the frame is increased by a factor of 3, keeping the number of turns on the coil per unit length of the frame same, then the self-inductance of the coil is. So it will be increasing or decreasing by some factor, and we are going to find out that particular new value of, by not a new value, but by how much amount it increases or decreases. So we start with the basic formula for the self-inductance. So we know that our self-inductance L is given as mu naught n square A multiplied by L, where mu naught is the permeability, n is the number of turns, A is the area enclosed by the coil, and L is the length of the coil. So we can divide this entire question in, you can say, two parts: initial setup, and then we can say by when it is increasing by the factor of 3. So we can say in initial setup, the area of triangle. For that we assume that it is given as equilateral triangle and its shape, its side is given as A. Okay. So we say side length is equal to A. So you can say the area, if written as capital A, will be equal to square root of 3 divided by 4, and it will be our A square. So it means, so in the initial setup, we are going to calculate the initial self-inductance. Initial self-inductance. And the self-inductance, we already know the formula, mu naught n square A upon L. So in this case, we are mainly interested in the L, that's the length of the coil. So let us say L initial is the, we can say, initial length of the coil. Initial length of coil, and that will be equal to the perimeter of the triangle. Perimeter of triangle. So we can write our L initial will be equal to 3A because side is given as A. So we can write the initial self-inductance, that is our L initial will be equal to mu naught n square, and here we have area, we just wrote it as square root of 3 divided by 4, and we have this as A square, and multiply by length initial, that is 3A. Now it says that the linear dimension is increased to 3 times. That is our final condition, final setup rather. So we can say it is as a final setup, and it says that linear dimension are increased to 3 times. Therefore, the new parameter let us call that P prime, that will be equal to 3 multiplied by initial parameters, that is 3A, so this comes as 9A, and new area let us call that A prime, and A prime will be equal to square root of 3 divided by 4, and this comes as 3A square. And if we solve this, we can write this as 9 square root of 3, 4, and this comes as A square. And new, you can say final length of the coil will be equal to our, that is parameter, which is our 9A. So you can say final length of coil, that is L final, will be equal to 9 times A. Now we can calculate the final self-inductance. final self-inductance, and we simply modify the formula. We can write L final, which will be equal to number of turns are same, and square root of 3 divided by 4, and this we have a square, and length is our 9 times a, and we can find out the ratio. So we can say L final upon L initial will be equal to, this comes mu naught n square, and we have 9 square root of 3 divided by 4 a square, 9 times a, divided by mu naught n square, and here we have 3 root divided by 4 a square and 3a. And most of the terms are going to cancel out here. This a square, a, 4 and 4 goes away, and this root 3 and root 3 goes away. So this comes as 3, and we are left with 9 and 3 only. So this can be written as 9 times 3, which comes as 27. So we can say our final inductance is equal to 27 times initial inductance. And the option that is the correct one is increased by a factor of 27, that is option number C is correct. Option C is